Welcome to This Explainer. Today, we're diving into a really fascinating chapter on data, its source, compilation, and honestly, the sheer power of numbers. We're literally surrounded by statistics every single day, right? From the weather app on your phone flashing city temperatures to complex maps tracking population growth. But understanding data, it's not just some dry academic exercise to memorize for a test. In our modern world, it is pretty much a survival skill. We're going to break down the core concepts from this chapter to figure out exactly where these numbers come from, what they actually mean, and how to process them logically so, well, you don't get fooled. So let's jump right in with a story from the text. It's a bit dark, but it absolutely hits the nail on the head. Imagine a man traveling with his family, and they arrive at a river they need to cross. He wants to play it safe, so he wades in and measures the depth at 4 different points: 0.6, 0.8, 0.9, and 1.5 meters. Doing some quick mental math, he calculates the average depth to be 0.95 meters. Now, his kid is exactly 1 meter tall. Looking at that average of 0.95, the dad confidently decides, hey, it's safe to cross. But tragically, the child drowns. Why did that happen? Well, the father relied completely on a simple average. He totally ignored the raw data distribution, specifically that one massive 1.5 meter drop-off, which was way over his kid's head. Sitting on the riverbank, he pondered a famous saying, Lekov joka thahe to bacha duba kahe. Basically, why did the child drown when the average depth was totally manageable? This story perfectly captures what we call a statistical fallacy. It's a huge wake-up call, showing why relying purely on raw averages without seeing the whole picture can be incredibly dangerous. It can completely detach you from reality. Here is our roadmap for today's explainer. 1. The danger of averages. 2. What is data really? 3. Hunting for sources. 4. Taming the raw numbers. And 5. Finding the patterns. Part 1. The danger of averages, beyond the fallacy. Because of the very real dangers we just talked about, entire disciplines, like geography, have completely transformed. They've shifted away from just giving a qualitative description, like casually observing that an area gets a ton of rain, to a highly precise quantitative analysis. If we want to study cropping patterns today, we need hard numbers, crop yields, irrigated areas, exact rainfall, fertilizer usage. Or think about city growth. You can't just say a city is getting bigger. We have to actually measure population density, track migration, and look at occupational salaries. Precise mathematical tools aren't optional anymore. They are absolutely essential. Moving on to part 2. What is data really? So let's define our terms. What exactly is data? Basically, data refers to raw numerical measurements from the real world. A single measurement, by the way, is called a datum. So if a news report says there was 20 centimeters of continuous rain in Barmer, that is data. But, and this is a crucial distinction, information is different. If raw data is just a big chaotic jumble of numbers, information is the meaningful answer we extract from it. Information is what you get when you logically deduce or mathematically calculate something from that raw data to actually answer a question or spark a new one. And that leads us to the data life cycle. We generate so much data globally today that raw numbers just sitting there on their own are pretty much useless. They have to go on a journey. It starts with collection, then moves to tabulation, followed by processing, and finally presentation. It's only by moving step by step through these precise quantitative techniques that a raw number can transform into actual, actionable information. Which brings us to part 3, hunting for sources. Before we can process anything, we need to know where to dig up these numbers. The chapter outlines 2 main ways to hunt down data, and knowing the difference is key. Primary sources are when data is collected for the very first time by an individual or an organization. You're getting your hands dirty and finding brand new facts yourself. Secondary sources, on the flip side, are when you pull data from already published or even unpublished records. You're basically leveraging reports that some other agency has already put together. Now, if you are out in the field gathering that primary data, you've got a few options. You might use personal observations, do interviews, or hand out questionnaires. Let's say you're studying natural vegetation or urban settlements firsthand. You definitely use personal observation. But the text makes a massive point here. If you're observing things yourself, you absolutely must have a solid theoretical understanding of the subject and a strictly scientific attitude. You have to ensure an unbiased evaluation. You can't just guess out there. It has to be completely methodical. But look, if you don't have the time or the resources to trek out into the field, secondary data is going to be your best friend. It lets us stand on the shoulders of giants.
You can use published reports from national and international agencies or dig into private documents. There is an absolute treasure trove of knowledge in unpublished reports from companies, trade unions, or residents' welfare associations. All that private and public data is just sitting there, already compiled, waiting to be processed.
All right, part 4, taming the raw numbers. So, you've gathered all your sources. What happens when you're faced with a massive, incomprehensible jumble of numbers? Enter the statistical table. It's one of the simplest but literally most powerful devices we have for drawing meaningful inferences. A statistical table is your ultimate cleanup tool. By systematically arranging data into neat columns and rows, it takes a chaotic mass of numbers and creates order in a super compact space. It's designed specifically to simplify presentation, so anyone looking at it can quickly locate what they need and make direct comparisons. And finally, part 5, finding the patterns. Now that our data is nicely tabulated, we start finding the hidden stories. We can take a bunch of chaotic individual data points, like, say, test scores from a class of students, and organize them to reveal a clear pattern. The chapter calls this creating a frequency distribution. We take all those individual scores and bin them into classes or groups, like 0 and under 10 or 10 and under 20. The number of times an observation falls into one of these specific groups is called its simple frequency, which we represent with a little f. Suddenly, instead of staring at dozens of random test scores, you instantly see exactly how the bulk of the class performed. It's a total game changer. Another brilliant tool for finding patterns, especially when you're looking at changes over time, is the index number. Let's quickly demystify this formula. Say you want to track India's iron ore production over a few decades. Trying to compare raw millions of tons in your head is tough. So you pick a base here, let's say 1970, and you set its production value to exactly 100. Then, for any current year you're looking at, you divide its production by the base year's production and multiply it by 100. It's this incredibly elegant calculation that lets you instantly spot percentage growth or decline relative to that starting point. And then there's a slightly more advanced technique, cumulative frequencies. Instead of just looking at the simple frequency of one isolated group, we add them up successively. You can organize these as less than or more than distributions. So if you want to know exactly how many students scored less than 40, you just add up all the simple frequencies of the groups below that threshold. When you plot these cumulative frequencies on a graph, they create these sweeping curves called ogives. It makes complex data boundaries instantly readable at a glance. And that wraps up our explainer for today. We've traced the whole journey, how data goes from a wild, raw measurement out in the field, all the way to a precisely tabulated and mathematically processed piece of information. The big takeaway from the chapter is that data is supposed to reflect the real world, but that only happens if we collect and process it the right way. So I want to leave you with a question. The next time you see a quick statistic flashing on the evening news, will you just blindly accept the simple average? Or will you remember the story of the river, dig into the raw data, and avoid falling for your own statistical fallacy? Keep questioning the numbers and keep learning.